All right, so you may remember Thevenin and Norton from EE220. I'm just going to overview or review it really quickly. So first of all, I just want to talk about what a Thevenin and a Norton equivalent circuit look like. If we recall from the DC case, our Thevenin equivalent circuit was a voltage source, DC voltage source in series with some resistance. And that would be V Thevenin here and R Thevenin here. And basically what that meant, let's go ahead and just draw it out and kind of review. If I had some circuit here, this is my circuit, it could have any number of voltage sources, resistors, this is from EE220, and then I connect some load resistor, let's call it RL, to that circuit. Obviously, I would measure some voltage across that load resistance, V, we can call it VL, and I would obviously measure some current through that load resistance, right? Well, what the Thevenin equivalent circuit tells me is that if I connect that same load resistor, so if I were to literally grab this load resistor and plug it into this equivalent circuit right here, I would read the exact same voltage VL and the exact same current through that resistor, even though I replaced all of this circuitry, which could be any number of sources and resistors, by a single voltage source and a single resistor in series. Okay, that's what the Thevenin equivalent circuit tells us, and that's why it's useful. We haven't discussed or we haven't reviewed how to find it yet. I'll do that in the next slide. But that's what the Thevenin equivalent circuit tells us. What is the Norton equivalent? Well, it's basically the exact same thing, except instead of replacing, so let's go ahead and draw this same exact thing. Copy it over to the other side. So again, I have some circuit with a load resistance, and I have some load voltage across it and some current flowing through it. Again, this is any combination of sources and resistors, really any combination of linear components. And so if I want to look at my Thevenin equivalent, it's a little bit different, because instead of replacing the circuit with a voltage source in series with the resistor, I replace it with a current source in parallel with a resistor. Okay, that's the Norton equivalent, where this source is called I Norton and this resistor is called R Norton. Okay, and let's recall that R Thevenin is always equal to R Norton. So that resistance is the same in both cases. That's source transformation. We talked about that previously. But again, what this circuit tells me is that if I had some load resistance connected to my circuit, the Norton equivalent for that circuit can be drawn such that there's a resistor in parallel with a current source. And if I were to connect that same load resistor out here, I would measure the same load voltage and the same current flowing through it if I have the correct Norton equivalent circuit, okay? So that's Thevenin and Norton. How do we find them? Here's the steps. I have this slide. This is kind of the same slide I used in EE220. The first thing we do is we remove the load resistor from the circuit. So let's say this is our circuit right here. We would remove this load resistor, so we'd be left with just the circuit itself, right? That's step one. Oops. Step two is, if we're trying to find the Thevenin voltage, we use circuits method, so anything we can use, nodal or mesh or KVL or KCL, to find the open circuit voltage. And what is the open circuit voltage? It is the voltage across the load terminals when the terminals are open. So in this case, if I have my circuit right here, and I removed my load resistor, right? And I'm trying to measure the voltage here, that is my open circuit voltage, okay? So the open circuit voltage is I would figure out what is the voltage between those two terminals, and that would give me my voltage, my open circuit voltage, which is then going to be my Thevenin voltage in my Thevenin equivalent. These two are equivalent to one another. So that's the open circuit voltage. Keep going the wrong way. If I'm trying to find the Norton current, I do the opposite, not the opposite, but instead of having the load open and trying to determine the voltage across it, I actually short these two terminals together, and then I try and determine the current through it. That is my short circuit current. And then that, whatever I measure there, that is my Norton current, okay? So that's how I determine my open circuit voltage, my short circuit current. Once I have two of the three quantities, I don't need any of the others. I can use the first two to find the third one, but if you really wanted to go through and find the resistance, all you have to do is short all the voltage sources, open all the current sources, and then find the equivalent resistance between the load terminals, okay? So what that basically means is, let's say that my circuit looks something like this. I have a voltage source, a resistor, another resistor, and then my load was out here, right? That's where my load was that I disconnected. I'd basically draw a short across this resistor, or this battery voltage source, and then I would look at what is the resistance looking into this terminal. So it would be, I would see this resistor first, and then I have, kind of a split here. But since this is a short, all the current would take this path. So only this resistor would be my equivalent resistance. That's how you find the Thevenin or the Norton resistance. It's the same for Thevenin and Norton. Again, this is all review from EE220. The last thing I want to say on this is that for an AC circuit, instead of a DC source and a Thevenin resistance, and the same going for the Norton, where there's a DC current source and a Norton resistance, we now can have an AC Thevenin voltage and an impedance Z Thevenin, right? That's going to be our Thevenin equivalent circuit. Now, draw a box around that. Oh. So this is our AC Thevenin equivalent circuit. Why is it giving me such a big box? That's not what I'm drawing. Look at that. It's like snapping to this much higher area where I don't want it. I have no idea why it's doing that. Okay, I'm not even going to box it then. I'm just going to leave it. So that's my Thevenin equivalent circuit, and my Norton equivalent circuit would be an AC current source. So this would be I Norton in parallel with my Norton impedance here, and then my load terminals are here. So that's our review of Thevenin and Norton. The steps are here. Probably not going to ask you to solve any of these. I just wanted to cover it since I said I would, but I'm starting to think that this module has gone on quite a bit too long. So I'm going to go ahead and stop with the Thevenin and Norton review. I'm going to overview source transformation really quickly, and then I'm going to show an op-amp circuit, some op-amp examples, because I think that those are actually very important in AC circuits, and then we will be completely done with this module. Okay, so I'm going to go ahead and wrap this one up, and let's go ahead and move on to source transformation.